You know, I was staring at a loading bar today, just watching a model generate some code for a project I'm on.
The classic developer experience.
Exactly. And it just hit me. We always talk about these LLMs like they're, these magic brains. We call them code architects or digital geniuses.
Right.
But we rarely stop to ask the most basic question, which is, how do they actually read?
Right. Because you don't just hand a physical book to a computer and expect it to, I don't know, hallucinate a summary.
Exactly. I can't just feed it raw English or Python for that matter. It has to be translated. And I think most people, myself included, kind of assume that translation is the boring part.
The plumbing.
Yeah, just chopping up words. But digging into the research for today, it turns out that chopping up words is actually where the war for efficiency is being won or lost.
It is definitely not boring. I mean, it is the bottleneck. If you get this part wrong, the tokenization, it doesn't matter if you have a trillion parameters or the best data. Your model will be slow, it'll be stupid, or it'll just run out of memory.
So that is our mission for this deep dive. We are looking at the math behind the magic. We're going to break down the big three algorithms: BPC, WordPiece, and SentencePiece.
The big three.
We are going to actually look at the complexity notation. Yes, we are doing big O today. Brace yourselves. And we're going to answer the big question. Is a bigger vocabulary actually better?
Spoiler alert, not always. It is a massive game of trade-offs.
Okay, let's start with the absolute basics, though. When I type "Hello World" into a chatbot, what's the very first thing that happens?
Before the neural network even wakes up, your text hits the tokenizer. The tokenizer's job is to turn your messy, flexible human language into a rigid list of integers, numbers.
Because neural networks are just giant math machines.
Exactly. They don't understand A or B. They understand 1 and 2.
And the most intuitive way to do this, and this is what we did in the old days of NLP, was just to assign a unique number to every single word, right? Apple is 1, banana is 2.
Right. Word-level tokenization. But that breaks almost immediately. Think about the sheer number of words in English, let alone if you start adding other languages. You end up with a vocab list that's millions of lines long.
And what happens when someone types something new, like Instagram back in 2005?
Hey.
If your model doesn't have a number for that, what happens?
It just hits a wall. It sees an unknown token, usually written as UNK in brackets. The model effectively goes blind to that word. So it's way too brittle.
Okay, so on the flip side, you could just assign a number to every letter, A, B, C.
You could, but then the model has to learn that APPLE means a fruit. That's making it do way, way too much work.
Right, character level is too granular. You lose the meaning.
Exactly. So we need a middle ground, something that handles words that it's never seen before, but recognizes common words instantly. Which brings us to the reigning champion of tokenization.
Yeah.
Byte pair encoding, or BPE.
This is the big one. This is what GPT-4 uses, isn't it?
Correct. GPT-4, and specifically the tick token library from OpenAI, relies on BPE. But here's a fun fact. BPE wasn't actually invented for AI. It's a data compression algorithm from the 90s.
A compression algorithm. So how does that teach a robot to read?
It's all about frequency. BPE starts with the assumption that you know nothing about language. No words, no grammar. You only know characters. A, B, C, D.
So at step 0, if I feed it the phrase deep dive, it just sees DEEP space, DIVE.
Right. Every character is a unique token. But then it scans your entire data set, let's say all of Wikipedia, and it just looks for the pair of characters that appear next to each other most often.
In English, that's probably T and H.
Almost certainly. So BPE says, okay, T and H are basically inseparable, let's merge them. Now, V is a single token with its own ID number.
And it just does this over and over.
Iteratively, millions of times. It merges E and R to make R. Then maybe it merges B and E to make D. It keeps building larger and larger chunks based solely on how often they show up.
I really want to walk through the example from the notes because this made it click for me. The low, lower, lowest example.
Ah, yes, the classic textbook case.
So let's imagine our entire language is just 3 words: low, lower, and lowest. BPE starts with just letters. LOWERST.
Right, 7 initial tokens.
It scans the text. It sees L and O are next to each other 3 times, once in every word. That's the most frequent pair. So merge, we get a new token, low.
So your vocab is now the individual letters plus low.
Next pass, it sees low is followed by W 3 times, merge again. And now we have low as a single token.
And this is the crucial moment. We've essentially learned the word low just by looking at patterns. But now look at what happens with lower and lowest.
Right, lower is now the token low plus E plus R. BPE will probably see E and R together often enough to merge them. So lower becomes 2 tokens. low, and error.
Lowest becomes low and est. This is the superpower of BPE. It creates a vocabulary where common words are single tokens, but complex or rare words are built out of Lego bricks.
That's a great analogy. The Lego bricks.
Yeah, it handles morphologically rich languages beautifully.
Mm.
If I invent a word right now like GPT-ification, the model has never seen it, but it has tokens for GPT, ific, and ereditation. You can piece it together and probably guess the meaning.
It's so elegant, but, and I feel like there's always a but in these engineering stories. Simply counting pairs seems a little, I don't know, crude, doesn't it?
It is crude.
Just because two letters sit next to each other a lot, does that really mean they should be a token?
That is the exact critique that led to, well, the main rival approach, WordPiece.
Which is what BERT uses.
Yes, Google's BERT used WordPiece, and you hit the nail on the head. BPE is a frequency algorithm. It asks, is this pair popular? If yes, merge it.
Right.
WordPiece is a likelihood algorithm.
Okay, that sounds significantly more expensive to calculate.
Oh, it is, significantly. Instead of just grabbing the most frequent pair, WordPiece asks a much deeper question. If I merge these two tokens, does it increase the likelihood of my training data?
Wait, hold on. Likelihood of the training data. What does that actually mean in this context?
Think of it like a prediction game. WordPiece basically trains a tiny, simple language model at every single step of the tokenization process. It tests a merge, say, combining U and N into UN, and it checks the math. It asks, does having UN as a token help the model predict the text better than keeping them separate?
So it's running a mini simulation for every single potential decision.
Essentially, yeah. Let's look at the word unbreakable.
Okay, unbreakable.
BPE might just chop it up based on whatever letters it sees most often. Maybe it splits it as able, because those chunks appeared in other random words. It doesn't care about meaning, just popularity.
But WordPiece is looking for the split that holds the most information.
Right. It might test merging UN and break. It calculates the likelihood. If adding the token UN increases the probability of the dataset more than adding NB or UB, it chooses UN. It's trying to maximize the information density of each token.
That sounds incredibly smart, but my immediate thought is that sounds incredibly slow to build.
It's painfully slow to train. The complexity is roughly O of N times V per iteration.
Okay, let's decode the math. O of N times V.
Right, so N is the size of your input data, which could be gigabytes and gigabytes of text, and V is your current vocabulary size. For every iteration, just to make one decision about what to merge, you have to check possibilities against all that data.
Wow.
When you were building the vocabulary initially, it takes huge computational horsepower.
But that's a one-time cost, right? Once Google trains the BERT tokenizer, I can just use it.
Exactly. And this is the twist. Inference actually using the tokenizer is fast. When WordPiece reads text, it uses a greedy approach. It just tries to grab the longest subword it recognizes from its list.
So if it sees unbreakable and unbreakable is on its list, it grabs it. If not, it looks for unbreak.
Right. It wants the biggest chunk possible. That complexity is closer to O of M times N, where M is the max word length. In practice, it's very fast.
So BERT used this likelihood approach. What was their vocabulary size?
BERT settled on about 30,000 tokens.
That seems small. I mean, we just said GPT-4 is over 100,000. Why would they restrict it to 30,000?
That brings us to the great trade-off, which we will definitely get to. But before that, there's a flaw in both BPE and WordPiece that we have to address.
What's the flaw?
They both generally assume that words are separated by spaces.
I mean, aren't they? Hello, space world.
In English? Sure. In Chinese? No. Japanese? No. Even in German, where you can mash words together into these massive compounds, relying on spaces to pre-split your text is a nightmare.
Huh. I hadn't thought about that. If the algorithm relies on spaces to know where a word even starts, it just fails in languages that don't use them.
Enter SentencePiece.
Mm-hmm.
This was the breakthrough used in models like Albert and T5.
SentencePiece. Okay, that sounds like it fixes the word problem.
It essentially says, forget concepts like words or sentences. Let's just treat the input as a raw stream of Unicode characters.
So a space isn't a separator anymore.
Nope, a space is just another character. In fact, if you look at the raw output of SentencePiece, you'll often see this low underscore character everywhere. That represents a space. It treats the space between deep and dive with the same mathematical respect as the letter D.
That feels so much more robust, especially for coding or just messy data from the internet.
It is, and SentencePiece often pairs this with a strategy called unigram. And this is where the logic completely flips. BPE and WordPiece are bottom up. They start with letters and merge up. Unigram is top down.
Meaning it starts with words and breaks them down.
It starts with everything. It initializes with a massive vocabulary, every possible substring it can find, and then it starts killing them.
It's the Marie Kondo of tokenization. This token does not spark joy. Delete it.
That's actually a perfect way to describe it, yes. It calculates which tokens contribute the least to the overall likelihood of the data, and it prunes them. It just throws away the bottom 10% or 20% in every pass until it hits the target vocabulary size.
That sounds incredibly rigorous.
It is. And here's where the math gets really beautiful. When it actually tokenizes a sentence, it uses something called the Viterbi algorithm.
I saw that in the notes. O of n times m squared.
The Viterbi algorithm is basically a way to find the absolute optimal path through a maze of probabilities. BPE is greedy. It just grabs the next best pair. Viterbi looks at the whole sentence and says, what is the statistically perfect way to chop this up?
So we have BPE, the merger, WordPiece, the predictor, and SentencePiece, the pruner. But knowing the algorithms isn't enough, right? You have to know how they break.
The gotchas.
Exactly. Because nothing works perfectly in the real world. What's the nightmare scenario for these?
Let's look at BPE again. Remember, it relies entirely on frequency. It wants to find pairs that repeat.
Right.
What happens if you feed it random noise?
Right.
Or a DNA sequence? Or just a string of characters where no pair appears more than once?
You wouldn't find anything to merge.
It would keep looking, and it can spiral in some implementations. But the real funny one is the opposite. Imagine a string of just the letter A repeating, say, 10,000 times. BPE might try to merge AA, then AMPA, then AAA. It creates these useless hyper-specific tokens. It's called vocabulary explosion. The worst-case complexity can actually hit O of n squared.
So instead of efficiency, you get a model that's trying to learn a unique token for the letter A written 512 times.
Precisely. It's a total waste of memory and compute. That's why engineers use techniques like vocabulary pruning or smart sampling of their training data. You have to make sure your tokenizer doesn't overfit to garbage.
Okay, let's get to the part that really surprised me in the research, the hardware impact. We established that BERT used 30,000 tokens. GPT-4 uses over 100,000. Why the huge difference? And don't just say newer is better.
It's not about newer. It's all about the embedding matrix.
The embedding matrix, that's the lookup table, right?
Think of it as the model's brain space reserved just for definitions. Every single token in your vocabulary needs a dense vector representation, a long list of numbers that explains what it means. If you have 100,000 tokens, that matrix is massive.
And that sits in the GPU memory.
It eats up huge amounts of VRAM. It is always there, taking up space before you even load the actual layers of the neural network.
I have some stats here from the deep dive that just blew my mind. It says that reducing a vocabulary from 100,000 down to 32,000, what does that do?
So if you cut the vocab size that drastically, you decrease the embedding layer's memory usage by up to 40%.
40%. That is massive.
It's huge. If you were trying to run a model on a phone or a laptop or you have a limited GPU budget, that 40% memory savings is the difference between the model running or crashing.
That makes the BERT decision make so much more sense. 30,000 tokens, they were optimizing for memory footprint.
Exactly. BERT was designed to be pre-trained efficiently. But here's the trade-off. What happens when you shrink the vocabulary?
Well, you have fewer words to choose from, so you have to use more tokens to say the same thing.
Correct. If extraordinary is in my 100K vocab, it's one token, one step for the model to process. If I shrink my vocab, I might have to split extraordinary into extra ordinries, 3 tokens.
So the model has to do 3 times the work for that one word.
The stats from our source are really clear on this. Dropping from 100K to 32K vocabulary increases the average sequence length by about 15%.
So inference is 15% slower just because there's 15% more stuff to read.
Roughly, yes. So here's the choice an engineer has to make. Do I want to save 40% of my memory with a small vocab? Or do I want to speed up generation by 15% with a large vocab?
That explains Roberta.
Right. Roberta came after BERT. They bumped the vocab from 30,000 up to 50,000. They decided, okay, we have better hardware now. Let's trade some memory back to get a bit more speed and nuance.
It's like a slider bar. You slide it one way for speed and the other way for memory efficiency.
And we can't forget nuance.
How does vocabulary size affect nuance?
This is a bit counterintuitive. Sometimes having a smaller vocabulary actually makes the model smarter about language structure.
Really? I would have assumed more words equals smarter.
Not always. If I have a unique token for run, running, runner, and ran, the model initially sees them as four totally unrelated IDs. ID 101, ID 500, ID 900. It has to learn through training that they are all related.
But if I chop them up?
If I have smaller vocab, running becomes run plus ning, runner becomes run plus nair, the model sees the token for run in both. It immediately knows, oh, these concepts are related to the base concept of running.
So smaller vocabularies can actually help the model understand the Lego nature of language. It forces what they call compositionality.
Exactly. But if you go too small, like just using characters, the model loses the forest for the trees. It spends all its brain power just assembling letters and misses the bigger meaning.
It's a Goldilocks zone. Too big, and you waste memory and lose connections. Too small, and you waste compute and lose context.
And that Goldilocks zone is always moving. GPT-4 went big, over 100,000.
Why?
Because context windows are getting bigger. If you have a 32,000 token limit in your prompt, you want those tokens to be as dense as possible. You want the United States of America to be one token, not five. That way you can fit more information into the prompt.
That is a great point. Efficiency isn't just about speed. It's about how much information I can shove into the model's short-term memory. If my tokenizer is efficient, my context window effectively gets larger.
Precisely. They prioritized information density and prompt capacity over VRAM usage because they have the massive GPU clusters to handle it.
So we've covered BPE's frequency merging, WordPiece's likelihood calculations, SentencePiece's unigram pruning. We've looked at the memory versus speed trade-off. It really changes how I look at these models. It's not just a black box. It's a series of very human, very strategic engineering choices.
Absolutely. There is no perfect algorithm. You can't just say SentencePiece is the best. It depends entirely on what you're building. Are you building a multilingual beast? Use SentencePiece. Are you building a memory-constrained chatbot for a phone? Keep that vocabulary small. Are you building GPT-5? Go huge.
I want to leave the listeners with a thought you mentioned. We're seeing models get bigger and bigger, trillions of parameters, but we're also running into a hardware wall. We can't just keep buying H100s forever. Do you think the pendulum will swing back? Will we stop expanding vocabularies to shorten sequences and maybe go back to smaller, hyper-efficient token sets to save memory?
That is the big question. There's actually some fascinating research going into token-free models right now.
Token-free?
Models that operate directly on the bytes, no tokenizer at all. It reads the raw binary data. It's extremely computationally heavy at the moment, but if we crack that, we eliminate this entire layer of complexity. No more out-of-vocabulary errors, no more morphology problems, just raw data.
A pure digital brain reading, raw binary. That is both terrifying and exciting.
It's the next frontier. But for now, yep, we're stuck with our Lego bricks.
Well, that's all the time we have for today. Next time you're typing a prompt into your favorite AI, just remember the invisible meat grinder that is chopping your words into numbers before the magic can even happen.
It's all just math in the end.
Thanks for listening to The Deep Dive. If you enjoyed this, hit that like button, leave a comment, maybe tell us which tokenization algorithm you identify with most. Are you a greedy BPE or a statistical sentence piece?
I'm definitely a SentencePiece.
I know it! Catch you next time.